Hello everyone and welcome to our webinar. Today's webinar is called Zero-Emission Vehicle Awareness Series 1. We are joined today by Logan Hoyland. Logan is the Project Associate at the Municipal Climate Change Action Center, working with sustainability services at Alberta municipalities. Logan joined the Municipal Climate Change Action Center in Alberta municipalities in 2022 and currently helps deliver the Action Center's electric vehicle charging program and electric vehicles for municipalities program throughout Alberta. Logan has an alternative energy technology diploma from NAIT and a Bachelor of Education from the U of A. Logan is motivated to increase awareness and knowledge about zero-emission vehicles and their role in combating climate change. I'm going to be handing it over to Logan, but I wanted everyone to know that if you do have questions, please leave them in the chat box down below, and we'll do our best to get back to you. Over to you, Logan.
Logan Hoyland, and welcome to the first webinar in the three-part webinar series about zero-emission vehicles, zero-emission vehicle myths and misconceptions, and the future of zero-emission vehicles in Canada. These webinars have been developed and are being presented by the Municipal Climate Change Action Centre on behalf of Eco-Canada through the federal government Zero-Emission Vehicle Awareness Initiative. The Municipal Climate Change Action Centre respectfully acknowledges that we live, work, and play on the traditional and ancestral territories of many Indigenous, First Nation, Métis, and Inuit peoples. We recognize that what we call Alberta is the traditional and ancestral territory of many peoples, presently subject to Treaties 4, 6, 7, 8, 10, and 6 regions of the Métis Nation of Alberta. This presentation is being delivered from Edmonton, Alberta. We respect the courageous and resilient community leadership of Indigenous people of all ages, knowledge keepers and elders, those who are still with us today and those who have gone before us. We make this acknowledgement as an act of reconciliation, gratitude, and commitment to pursuing an inclusive, collaborative, and respectful path towards building strong communities. Government of Alberta. The Action Centre provides funding, technical assistance, and education to Alberta municipalities, nonprofits, and schools in addressing climate change. Since 2009, we have managed a variety of programs that have made a significant impact throughout Alberta, including work with 389 unique participants to complete 830 projects and catalyze $155 million in clean energy cost lifetime savings. Eco-Canada's vision is to build the world's leading environmental workplace. Eco-Canada seeks to help environmental workers succeed at each step of their career journey. To do this, Eco-Canada has developed several programs tailored to individuals at different stages of their careers. Taking a look at today's agenda, there are 7 key topics we will be addressing. First, what are internal combustion engine vehicles? 2, electric vehicle types and their characteristics. 3, a brief overview of the history of EVs and their rapidly increasing presence. 4, a quick introduction to hydrogen fuel cell vehicles and how they differ from fully electric vehicles. 5, the differences between internal combustion engines and electric motors. 6, EV charging and the different types of chargers and their capabilities. And finally, an overview of EV cost savings and their environmental impact. Before we delve into zero-emission vehicles, it's first important to understand what internal combustion engine vehicles are. ICE vehicles account for roughly 95% of all the vehicles that are on the road in Canada today. ICE vehicles use either gasoline or diesel as their main source of energy. Gasoline or diesel is mixed with air inside the engine and combusted, which is like a small controlled explosion. The mechanical energy produced is then used to turn the wheels of the vehicle. A byproduct of combustion reactions is exhaust, which contains greenhouse gas emissions. Starting off, there are 3 electric vehicle types: hybrid electric vehicles, which cannot be plugged in; plug-in hybrid electric vehicles, which can be both plugged in and refueled; and battery electric vehicles, which can only be plugged in. Vehicles differ in the amount of electricity that they primary fuel source and their environmental impact. HEVs, or hybrid. HEVs are commonly referred to as only hybrids. A common example of a hybrid is the Toyota Prius. The term hybrid electric is misleading, as hybrids rely on fossil fuel such as gasoline as their primary source of energy. What differentiates a hybrid from a conventional internal combustion engine vehicle is that they have a small 1 to 2 kilowatt-hour battery pack that supplies electricity to an electric motor. The electric motor typically assists during vehicle acceleration, which is normally the most fuel-intensive part of driving. This reduces gasoline consumption and makes the vehicle more fuel efficient and environmentally friendly. When a hybrid electric vehicle brakes, electricity is produced via regenerative braking and the electric motor and is stored in the small battery pack. This is why hybrids are more fuel efficient in the city, as there is more frequent accelerating and decelerating, compared to city driving, where the vehicle maintains a relatively constant speed. The second type of vehicle are PHEVs, or plug-in hybrid electric vehicles. Plug-in hybrids are often mistaken as the same as hybrids. However, plug-in hybrids combine elements of conventional internal combustion engine vehicles and battery electric vehicles. A common example of a PHEV is the Toyota Prius Prime. Plug-in hybrids can be both plugged in, like a fully electric vehicle, and can also be refueled like an internal combustion engine vehicle. This allows the plug-in hybrid to use 2 primary sources of energy. Typically, plug-in hybrids have a medium-sized battery pack that stores around 8 to 14 kilowatt hours of electricity, which offers around 40 to 60 kilometers of pure electric range. Depending on the plug-in hybrid type and brand, some allow the driver to drive in fully electric mode. Once the battery is depleted, the plug-in hybrid then functions as an internal combustion engine vehicle and operates solely on gasoline. Some plug-in hybrids use the stored electricity throughout driving to increase fuel efficiency. Like hybrids, plug-in hybrids utilize regenerative braking to produce and store electricity. However, unlike hybrids, plug-in hybrids must be plugged in to fully charge the onboard battery pack. Battery electric vehicles, or BEVs, are commonly referred to as electric vehicles, or just EVs. Electric vehicles operate solely on electricity and can only be plugged in with specific EV plugs. Electric vehicles have a battery pack that ranges in capacity from 50 to 90 kilowatt hours, which provides around 300 to 500 kilometers of range, depending on vehicle type and driving conditions. Unlike internal combustion engine vehicles, EVs do not have an engine and therefore do not produce greenhouse gas emissions during operation. Rather, EVs typically use either 1 to 2 electric motors, which use electricity from the onboard battery pack. Electric motors typically operate at efficiencies of greater than 75%, meaning that around 75% of the electricity that is sent to the motor from the battery pack is actually used to turn the wheels. Finally, another key distinction between EVs and internal combustion engine vehicles is that EVs have considerably fewer moving parts and therefore significantly less maintenance. Typically, EVs have a higher purchase price compared to ICE vehicles. However, over the past 5 years, EV prices have been trending. At this table, you can see characteristics of internal combustion engine vehicles, hybrids, plug-in hybrids, electric vehicles. Plug-in hybrid vehicles combine all the elements of internal combustion engine vehicles and battery electric vehicles, while the characteristics of internal combustion engine vehicles and battery electric vehicles are opposite. The only vehicle type that does not produce greenhouse gas emissions during operation are battery electric vehicles. Looking at a few real-life examples in this table, you can see the expected gasoline and electric ranges of a few 2022 Hyundai vehicles. The Hyundai Elantra HEV uses a small battery pack to supplement driving and improve fuel efficiency, and has a gasoline range of around 885 kilometers. The Ioniq PHEV has both an electric range of 46 kilometers and a gasoline range of 950 kilometers. Finally, the battery electric Kona has an entire electric range of 415 kilometers. These ranges and efficiencies are from fueleconomy.gov and are representative of ideal driving conditions. Looking at the history of electric vehicles, it's important to zoom out and consider the entire landscape and history of the vehicles. While vehicles play an integral role in society today, vehicles have only been around for around 150 years, and over that period have seen tremendous innovation and adoption. Today, upwards of 90% of Canadians drive internal combustion engine vehicles. However, electric vehicles were actually invented prior to combustion engine vehicles. In 1889, William Morrison created the first EV in the US, and over the next roughly 20 years, EVs rose in popularity and accounted for almost 1/3 of all vehicles on the road. However, in 1912, Henry Ford began the mass production of the Model T, a gasoline-powered vehicle which quickly became affordable and readily available. Over the next 100 years, abundant and affordable gasoline, as well as the mass production, resulted in the internal combustion engine vehicle becoming the popular and common vehicle type throughout the world. In 2000, Toyota released the first mass-produced hybrid, the Toyota Prius. The Prius offered a more fuel-efficient option compared to a conventional ICE vehicle. However, conventional internal combustion engine vehicles still dominated the industry. In 2006, Tesla Motors began to produce the first luxury fully electric sports car, the Tesla Roadster, which forced other automakers to begin looking into EVs and battery technology. Over the next 15 years, battery technology continued to improve while the prices of batteries and EVs dropped. As the impacts of climate change and the importance of sustainability began to play a more key role in day-to-day life, the pressure to adopt EVs has increased. In 2021, the Canadian government announced that all new light-duty vehicles sold by 2035 must be electric. This commitment was also backed by GM, who is committed to sell only electric vehicles by 2035. While internal combustion engine vehicles have dominated the vehicle market for over 100 years, EVs are finally becoming a more feasible and environmentally friendly option and have the backing of government and industry. Before we look more specifically into the functionality and feasibility of EVs, there is one other zero-emission vehicle type we will take a look at briefly, the hydrogen fuel cell vehicle. Hydrogen vehicles differ from fully electric vehicles as they utilize stored hydrogen as their primary fuel source, which in turn creates electricity and powers an electric motor. Hydrogen vehicles require hydrogen, oxygen, and a fuel cell. Hydrogen and oxygen are combined across the fuel cell, which produces heat, water, and electricity. The electricity is then redirected to an electric motor. Currently, there are many challenges that face the widespread adoption of hydrogen fuel cells. Most notably, producing clean hydrogen is very difficult and energy intensive. It is also difficult to store hydrogen and can be very difficult to transport hydrogen. Currently, hydrogen fuel cell vehicles are more suited for fleet use, such as city buses, where the bus completes the same route daily and returns to the same garage where hydrogen fueling infrastructure has been developed. Here you can see a hydrogen fuel cell. A fuel cell consists of three parts: an anode, which is cathode, positively charged, and an electrolyte, which separates the two. Hydrogen is fed to the negative anode and is separated into its parts with assistance from a catalyst. The electrons flow through a circuit which is connected to an electric motor, while the protons flow through the electrolyte and combine with oxygen at the cathode to form water. The byproducts of fuel cells are electricity, which is used to power the electric motor, water, and heat. Shifting back to EVs, to gain a better understanding of the mechanical differences between internal combustion engine vehicles and EVs, we'll take a deeper look into the characteristics of each. In 2021, roughly 90% of all new vehicle registrations were internal combustion engine vehicles, making them by far the most common vehicle type in the country. Internal combustion engine vehicles typically use gasoline or diesel, both fossil fuels, as their main source of energy. However, despite that nearly all vehicles in Canada today are internal combustion engine vehicles, the systems and components that convert gasoline or diesel into usable mechanical energy which turn the wheels are incredibly complex. In today's internal combustion engine vehicles, the drivetrain typically contains upwards of 2,000 moving parts, all of which work together in the process of converting energy stored in the fossil fuel into mechanical energy that can be used to turn the wheels. When looking at the diagram on the right, there are three main inputs required for a gasoline internal combustion engine. Gasoline, which is the main energy source, air, which is needed for combustion, and electricity, which triggers combustion. In the combustion engine, air and gasoline are mixed and undergo combustion via an electrical spark. Combustion can be thought of as a small but powerful explosion contained. The mechanical energy that's created from the reaction is then redirected to the wheels through a series of shafts and gearboxes. The byproducts of combustion is exhaust, which contains an assortment of greenhouse gas emissions, which in large quantities have a detrimental impact on the environment. Common internal combustion engines operate at approximately 16% efficiency, meaning only 16% of the energy stored in the gasoline is used to turn the wheels. The remaining 84% is lost as heat or sound energy. Next, we'll take a look at how EVs use electricity to turn the wheels rather than fossil fuels. Unlike internal combustion engine vehicles, EVs do not have an engine. EVs typically have either one or two electric motors located on either the front or rear axle. In an EV, electricity is stored in a large 50 to 90 kilowatt-hour battery pack as DC electricity. When the driver of an EV presses down on the accelerator, a signal is sent to a controller, which in turn signals electricity to flow from the battery pack to a DC AC inverter and to the electric motor. The electric motor then uses advanced circuitry, rare earth magnets, and electromagnetic fields to convert the electrical energy into mechanical energy, which turns the wheels. There are two main components in an electric vehicle, an electric motor, a stator, which doesn't move, and a rotor, which ultimately turns the wheels. As the process of converting electrical energy from the battery bank into mechanical energy in the electric motor is nearly instantaneous, EVs have a high amount of torque and can accelerate very quickly. Unlike internal combustion engine vehicles, EVs only have around 20 moving parts in the drivetrain, making the process of converting electrical energy into mechanical energy considerably less complex. Typically, electric motors are around 76% efficient at converting electricity energy into mechanical energy that turns the wheels. This is approximately 60% greater than internal combustion engine vehicles. One critical feature in EVs is the importance of cooling systems. As the battery pack and electric motors can create high amounts of heat during charging and operation, it is important to have adequate cooling systems to prolong battery life and motor life. Another key characteristic of HEVs, plug-in hybrid battery electric vehicles, is that they all share regenerative braking, one pedal driving. With one pedal, driver removes their foot from the accelerator, the electric motor is instantly reversed as electricity is no longer being supplied from the battery pack. This causes the motor to spin in the opposite direction and operate as a generator. The vehicle then begins to decelerate, and the energy that is produced from the deceleration is then fed back into the battery pack through the backward spinning electric motor. This process is what allows hybrids to produce and store electricity while operating. A major advantage of regenerative braking is that it reduces the dependency on traditional friction braking and prolongs brake life. If an EV driver is able to avoid using the brakes whenever possible and rely heavily on regenerative braking, the vehicle will have a greater fuel efficiency and an extended battery life. The diagrams on this slide overview the processes of EV acceleration and deceleration. During acceleration, the driver presses down on the pedal and a signal is sent to the battery pack, which in turn sends electricity to the electric motor, which turns the wheels. While with regenerative braking, the driver removes their foot from the pedal, which stops electricity from being sent to the battery pack to the electric motor. The electric motor then reverses direction and behaves like a generator, which in turn slows down the vehicle and sends electricity, which is produced during deceleration, to the battery pack. Now that we have a solid understanding of electric vehicle types and how electric vehicles and electric motors work, we'll now take a look at EV charging and the different charging levels. There are 3 levels of EV charging: level 1, level 2, and level 3. Level 1 charging is the slowest charge option and uses a standard 120 volt wall outlet. Level 1 charging adds around 5 to 8 kilometers of range per hour and is typically only used in emergency situations or when no other charging options are available. As level 1 charging is so slow, it is normally not practical for most EV drivers. The next level of charging is level 2. Level 2 charging is a medium charge option and uses either 208 or 240 volts, like a dryer wall outlet. Level 2 charging adds around 25 to 45 kilometers of range per hour, depending on the charger and vehicle type. Level 2 charging is best for when EVs are parked in the same location for upwards of 2 hours. Level 2 chargers are common in residential settings and workplaces where EVs will be parked for several hours at a time. The final charge level is level 3. Level 3 charging, or DC fast charging, is the fastest charge option and can typically charge an EV from 20% capacity to 80% capacity in around 30 to 40 minutes, depending on the charger and vehicle type. However, level 3 chargers often require phase 3 power in 480 volts, which can make the installation of level 3 chargers very expensive. Level 3 charging is often best suited for larger facilities or roadside locations where a driver may stop for only 30 minutes. There are 4 common plug types which all EVs use. The most common is the J1772 connector. The J1772 connector is used for level 1 and level 2 charging and is standard across all EVs. Second is the CHAdeMO plug that is only used for level 3 charging by Japanese-made EVs. Third is the combined charge system, or CCS, which expands on the J1772 plug for level 3 charging and is used by most American and European-made EVs. Almost all EVs sold in Canada today use the CCS plug type for level 3 charging rather than the CHAdeMO plug type. Finally, Tesla has its own proprietary charger, which is used on level 1, level 2, and level 3 charging. Teslas can use all plug types, but require a specialized adapter for the J connectors, CHAdeMO connectors, and the CCS connectors as well. Looking at this table, you can see the different characteristics of the different charger levels, including their required voltage, output current, plug type, and best uses. Going forward, a mix of level 2 in work and residential settings, as well as level 3 charge stations, will become increasingly important to meet the number of. Next, we'll look at the cost of ownership and the potential cost savings of EVs compared to conventional internal combustion engine vehicles. First, EVs have significantly lower operating costs compared to internal combustion engine vehicles. There are 3 key reasons for this. 1, EVs are roughly 60% more efficient than internal combustion engine vehicles. This means that you are using more of the energy that is stored in the electricity to actually move the vehicle rather than wasting it as heat or sound. The second is the price difference between electricity and gasoline. Depending on the cost of fuel and electricity, EV drivers can save up to 80% annually on fuel costs compared to driving an internal combustion engine vehicle. The third reason is decreased maintenance costs. As EVs have approximately 90% fewer moving parts compared to internal combustion engine vehicles, there is significantly less maintenance. On average, EV drivers can save around 50% annually on operational maintenance. The most notable components in EVs that require maintenance are brake pads, which last longer due to regenerative braking, tires, which can deteriorate quicker due to EV's heavier weight, and coolant, which is critical in keeping the battery cool and prolonging the life of the battery and the motor. Looking at a real-world example, we can compare the costs of ownership of an internal combustion engine vehicle 2023 Chevy Equinox and an electric 2023 Chevy Bolt EUV. Using fuel efficiency data from fueleconomy.gov, the average cost of gasoline in Edmonton, Alberta across 2021, which was roughly $1.24 per liter. The average cost of electricity in Edmonton across 2021, which was 16 cents per kilowatt hour, as well as the expected cost of maintenance per kilometer, we can see that per 100 kilometers of use, the cost of the Equinox is roughly $15 per 100 kilometers, while the cost of the Bolt EUV is around $5.28 per 100 kilometers, or roughly 1/3. Sticking with the same two vehicles, we can observe the total cost of ownership across 10 years of use. The Bolt EUV, shown in yellow, has a purchase price of $43,147. In this graph, the $5,000 federal EV incentive has been applied, bringing the purchase price down to $38,147. The Equinox, shown in green, has a purchase price of $31,000. Using the average daily distance driven by an Albertan, which is approximately 43 kilometers per day, we can see the cost of ownership over 10 years of use for both vehicles. Notably, after roughly 3.5 years of use, the total cost of ownership of the Equinox surpasses the Bolt EUV, despite the Bolt having roughly a $7,000 greater purchase price. After 10 years of use, the total cost of ownership of the Bolt EUV is roughly $7,300 cheaper than that of the internal combustion engine Equinox. The cost of ownership of EVs will continue to improve compared to internal combustion engine vehicles going forward as the purchase price of EVs continue to decrease and the cost of fossil fuels continue to increase. Finally, we'll take a quick look at the environmental impact of EVs. Most notably, EVs do not produce greenhouse gas emissions during operation, while internal combustion engine vehicles do. Despite that the electricity used in EVs often comes from a variety of sources, including natural gas, coal, hydro, solar, and wind, EVs typically emit approximately 50 to 60% less greenhouse gas emissions per kilometer when considering the entire life cycle of the vehicle. A more in-depth look at the environmental impact of EVs will be completed in webinar 2. And that brings us to the end of webinar 1. In webinar 2, we will be addressing common zero-emission vehicle myths and misconceptions, including EV range, EV environmental impact, battery degradation and battery recycling, impacts EVs have on the electrical grid, and the current charge in Canada today. Thank you everyone for attending this webinar presented by Eco Canada and the Change Action Center. If you found it useful.
Thank you, Logan. What an interesting and informative webinar. We do have a few questions. We will be answering those questions with our team after the webinar. I apologize for any of the echo that was happening. We will make sure that in the next series that is no longer an issue. Please join us for the next series is January 15th, and the third one will be February 15th. This recording will be made available to you within 24 hours in your inbox, so please look for it then. If you have any other questions, you can put that towards events@eco.ca. Again, that's events@eco.ca. Thanks a lot, everyone, and have a great day.